Define this new state function entropy, but I think it wouldn't be surprising at all if you're still a little bit confused as to what it has to do with molecules, because we've pretty much dwelt in the area of thermodynamics and of gas phase systems. So I want to begin to bring it together with molecules by using some of the concepts that we raised in the previous module. So in particular, we noted that the probability of being in a particular state J was related to the number of molecules that might be found in that state over n, which we then were able to find the most probable distribution and say that that was equivalent to an expression like this, where this little z is the molecular partition function. Now what I want to do is generalize this to a system. All right, so I want to talk about the probability of being in a system state J, and it's going to again be related to something similar to this expression here, but now we'll have system energies E sub j and the system partition function as the thing in the denominator. All right, so I know this looks a little bit scary, but I hope this will make sense as we go through it, and I'll try to keep the notation as simple as possible so that you can follow the concepts. Now, the essential idea that we're going to follow here is to start with the first law expression, which we've written like this, right, where we've got a differential change in the internal energy is equal to incremental changes in heat and work added together. But now I want to inject, if you will, a definition for U that's based upon our more microscopic view of things. Remember, we equated U with sort of an average energy that could be written as the sum over all the possible energy states in a system times the energy of those states times the probability that they occur. All right, and this is going to be my operational function to start with, but one would then plug these values in if we wanted to actually do something with this using the partition function and using the distribution of energy levels. But I want to leave it in this format right here for now because this will be easier for us to work with. Now, what I'm interested in looking at is actually not U itself, but its differential. So if I were to begin to exploit this differential relationship between U and incremental changes in heat and work, I'm going to need to start with this and take a differential of this expression. Okay, so if I do this, it's basically the same as, and let me make this an arrow, it's basically the same as doing this. I'm going to take a differential of this sum, but this sum is a series of products, and so if I take a differential of the product, I'm going to get a differential of the first term times the second plus a differential of the second term times the first. So I'll get something like this. All right, all I've done is take a differential of a product of functions. Now, it's useful to understand that in fact these functions have dependence upon macroscopic physical properties. For example, we know that the energies, at least the translational energies, are inherently functions of the volume. All right, we saw that in the expression for the energy levels of translation. We also know that the system partition function in some sense is going to be a function of the number of particles that we have in the system, the volume of the system, and the temperature of the system. All of these things come to play in defining the partition function of the system. So we can understand then that these quantities that we've written out here for the differential in internal energy are going to have some dependence on these quantities. So what can we do with this? All right, well, I'll first point out that a differential in energy, it really means that we have to have made a change in the volume somehow. And what we're talking about here is making a differential change in the positions of the energy levels themselves. So in this case, I might equate this differential in energy with a partial derivative with respect to volume, again with the other stuff held constant, so number of particles, temperature, and all of that held constant, times dV. So this is going to look a lot like a PdV sort of term, or an internal energy or internal pressure kind of term. Over here, we've got a differential that involves the probabilities. So what is that doing? Well, it's basically saying that we are going to make small changes in how the molecules are distributed among the various energy states. Now, maybe a better way to do this would be to draw a picture. Let's suppose I have a series of energy levels. Okay, so these are all energy levels for the system, quantum energy levels, if you will, and they have a certain population associated with them. Okay, and I'm just making up one, but let's say that this is their population, roughly speaking. If I want to talk about a change in the positions of the energy levels, then I may not have them spaced quite like this. Maybe that looks like this, where I've simply changed where those energy levels occur, but I haven't necessarily changed the distribution of molecules in those energy levels. And I'm trying to reproduce it as best I can here. All right, so this would be a change due to a change in the energy levels. But if I were instead to keep those same energy levels, and I'm trying to do that the best I can, but simply change the way they're populating these various states, something like that, then what I'm doing is making a change in those populations. So that's what these two changes mean when I talk about them in this way. Well, what we can do is we can relate this change that I've got here, since it was related to changes in volume. This, in some sense, is like the incremental change in work. And indeed, in order to change the positions of the energy levels of a system, we have to do work on the system. We have changed the system in some sort of physical way, which is akin to the work that we've done. Likewise, if we change the probabilities of molecules being in various states, that's like changing the distribution, but the simplest way to do that is to change the temperature. So in some sense, this term here represents a change in the temperature or a change in the way we're going to distribute things, so it is really related in some ways to an incremental change in the heat. So we're going to make these associations more explicit. I'll write dq, and I'm going to say this is for a reversible process because we're making very microscopic changes, so they are, reasonably speaking, they will be something that can occur in a reversible fashion. And likewise, my change in work will be reversible, and it will be related to keeping the probabilities constant but changing the energies. And that change of the energies is something that could be carried out like this. So using this sort of definition for these incremental changes in these quantities for heat and work, it gives us a sort of different view as to exactly what those changes mean at a molecular level. All right, so if you think about it, if I've got a system of molecules and I'm performing work on that system, what am I doing? I'm actually, in some sense, changing the positions of their energy levels. If I heat that system up or I cool it down, I'm changing the way those molecules are distributed among those energy levels, but by heating and cooling, I'm not really changing where those energy levels are. So this gives us now a way to think about work and heat on a molecular scale, and we'll see that this will open up our view of what entropy means for molecules and give us some additional insight about that.